I was recently invited to TU Dresden to talk about the work we do on digital twins for civil infrastructure with application to pavements. And this is a short version of what was presented there. The first question that needs to be addressed is, what is a digital twin for infrastructure? And the definition I'm presenting here is something we came up with after reading the literature regarding digital twins, because the literature is quite diverse and there are many versions. A digital twin is a duplicate computational model of a sensed infrastructure, and this is done with continuous updating of model parameters and even possibly with the formulation itself. And the updating is based on sensor readings. Here is a schematic representation of the digital twin concept. We start with the physical or real domain. Here's the time axis, and there are two time instances that are shown here, time ti and time ti plus 1. Here we have a time ti, the infrastructure, and the environment surrounding it. And here we have a time ti plus 1, the infrastructure again, and the environment surrounding it. We also have sensors sensing the infrastructure and the environment. And the colors here indicate that there is a change in the readings of the sensors in the environment and in the infrastructure. Now we move to the digital domain. Here we have a computational model of the infrastructure, and as an input, the data coming from the environmental sensors are applied over the computational model. And we can also generate digital sensors. These are sensor readings that are created by the computational model itself at the location and with the same entity as the physical sensors in the real infrastructure. And the question is, did anything change in reality? Did the properties of the infrastructure change? Did the structure change? And that can be assessed via parameter updates or formulation updates, or the necessity for parameter updates and formulation updates. So if we continue the simulation and there is no problem in replicating the infrastructure sensor readings with the digital sensor readings, that means that there was no need to change the parameters and there was no need to change the formulation. But if there was any change, then these need to be updated, or the formulation needs to be changed. With respect to parameter updating, here's a scheme for doing so. So we have a computational model, we have the current set of parameters, and we have the environment applied over the computational model. And here we take the digital sensor readings and then we compare them with physical sensor readings. And this difference is then sent to an optimization algorithm that updates the parameters, and we do this again and again continuously. In the master project of Lucia Barishik, we were looking at updating algorithm that is based on a controller, a PID controller approach. Here's an example application for a digital twin. The example is for asphalt pavements, and what I would present now has been published recently in a conference. The title of the paper is a thermal digital twin for condition monitoring of asphalt roads, and it was co-authored by Lucia Barishik, myself, Asmus Carr, Adam Boyd, and Pavlos Zoulis. Here's a cross-section of a pavement system, an asphalt pavement system. Here you have the asphalt concrete, the base, and I'm not showing here the deeper soil layers. Here's the pavement surface. We had the access in the work to two highway sections that were instrumented with temperature sensors. We had the T1 temperature sensor near the surface, T2 a temperature sensor that is 6 centimeters below the surface, and a third temperature sensor buried 30 centimeters below the surface. And over time, these sensors were recorded. The overall duration of recording that we had access to was 5 years, where the sensors were and the data was collected in a database. So the thermal digital twin, for that purpose, we used T1 as a thermal boundary, T3 as a thermal boundary, and we generated a computational model based on the one-dimensional heat equation. In this model, the diffusivity is the only input parameter that was needed, and we recreated digitally the readings of the T2 temperature sensor at the depth of 6 centimeters. By comparing these readings, the digital readings with the real readings, we were able to update the thermal diffusivity of the model in order to ensure that the match is continuous. Here are the results. We have here the thermal diffusivity from the digital twin, and here we have the time from 2013 until 2018. As I said, 5 years. And the two highway sections exhibited a completely different behavior. So one of them, you could see that the thermal diffusivity was changing, was unstable compared to the other section. When we took a look at the surface pictures of the two sections, so the section that exhibited more tortuous diffusivity behavior had worse surface conditions. The asphalt was exhibiting raveling, and the construction joints were open, and there were also some cracks at the surface. And when we looked at the other section that was associated with a more constant thermal diffusivity, the asphalt surface was intact, and the construction joints were closed. So just to list potential utility of digital twins, first is what I would say, know your structure. With a digital twin, you can gather information also on unsensed locations, because the digital twin, the computational model, can complete the image of your structure, we cannot place sensors everywhere, and this is maybe the most reliable image of the structure in between the sensor locations. And that, of course, can be utilized for condition monitoring, as I showed that the diffusivity updates were also indicative of the fact that the asphalt surface was not in good shape. And as such, the digital twin approach can be used to support maintenance activities, both reactive activities where you're getting information in real time and are able and need to react quickly, and also monitoring long-term changes and utilize these long-term changes to plan for more long-term repair activities. This is under predictive decisions. The digital twin can also be utilized to explore hypothetical scenarios. We can torture the twin by exposing it to extreme environments, and non-standard materials can be replaced in the twin with existing materials to check behavior. And also we can simulate component failure and assess the overall behavior of the system. And lastly, I would say that the digital twin helps closing the loop with design and construction, because today there is very little information that goes back to the designers or to the constructors after opening the facility to users. Some fine points to conclude. There's a question of twinness level, which means how close is the digital twin to the its real twin, and that of course depends on the modeling assumptions that we are making. The sensors are limited; they never record precise or exact values, and also it depends on the updating frequency. Do we want our twin to replicate reality every second, every microsecond, or every week, or every month? As far as we could see from the literature, parameter updating is the most common approach, and formulation updating is not so common. Just to be clear about the distinction, so parameter updating is where, for example, you have an elastic component and there's some distributed damage in that component, so you decrease the elastic modulus to represent that distributed damage. Formulation updating, we can think about this when one of the components is completely broken or fractured, and then we have to remove that component from the system, and that requires a new formulation or new boundary conditions. Another point. Digital twins can be, in general terms, be seen as made of two types. A child twin, where we are twinning the construction, the infrastructure while it is under construction, and then there is the adult twin when the construction is ready, or the infrastructure is ready for usage, and then we are twinning the behavior or the conditions under operation. Thank you very much for your attention, and feel free to check out the other videos in the channel.